Welcome to the world of C++ sorting algorithms. In this presentation, we will explore efficient techniques for organizing data in specific orders. Sorting is a fundamental operation in computer science, and mastering these algorithms will greatly enhance your problem-solving skills. Let's begin with bubble sort. Bubble sort is a straightforward comparison-based algorithm that repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. It's easy to understand and implement, but not very efficient for large datasets. The time complexity of bubble sort is order of n squared. Its space complexity is order of 1, and it is a stable sorting algorithm. Here's the C++ implementation, demonstrating how adjacent elements are compared and swapped. Next, we'll discuss selection sort. It is an in-place comparison sorting algorithm that divides the input list into two parts, a sorted sublist and an unsorted sublist, then repeatedly finds the minimum element from the unsorted sublist and moves it to the sorted sublist. Selection sort is another simple algorithm, but it generally performs better than bubble sort by reducing the number of swaps. Its time complexity is order of n squared. The space complexity is order of 1, but it is an unstable sorting algorithm. Key characteristics include simple implementation, performs well on small lists and fewer swaps than bubble sort. Now let's look at the C++ implementation. Now let's explore insertion sort. Insertion sort is a simple sorting algorithm that builds the final sorted array one item at a time. It is efficient for small datasets and is often used as part of more sophisticated algorithms. Insertion sort works well for small datasets and nearly sorted arrays. Its best case time complexity is order of n, average case time complexity is order of n squared, and space complexity is order of 1. Ideal use cases are small datasets, nearly sorted arrays, and online algorithms like stream processing. Here is the C++ implementation which builds the sorted array by inserting elements into their correct positions. Moving on, we will explore merge sort, an efficient, stable, comparison-based divide-and-conquer algorithm. Consistently performs order of n log n operations regardless of input data. Merge sort is a more efficient algorithm that uses a divide-and-conquer approach. Its time complexity is order of n log n, and its space complexity is order of n. Also, it is a stable sorting algorithm. The key principle is to divide the array into halves, recursively sort them, then merge the sorted halves back together. Here's the C++ implementation of the merge function, which merges two sorted arrays into one. Let's learn about quicksort. It is a highly efficient divide-and-conquer algorithm that selects a pivot element and partitions the array around the pivot. Quicksort is known for its speed and efficiency, especially on average. The average case time complexity is order of n log n, worst case time complexity is order of n squared, and space complexity is order of log n. Some of the advantages are in-place sorting that is low memory usage, cache-friendly, and faster than merge sort for arrays. Here is the C++ implementation, highlighting the partition and quicksort functions. Now we will learn about heap sort, a comparison-based sorting algorithm that uses a binary heap data structure. It divides the input into a sorted and an unsorted region, and iteratively shrinks the unsorted region. Heap sort is efficient and has a guaranteed time complexity. Its time complexity is order of n log n, space complexity is order of 1, but it is an unstable sorting algorithm. A key concept is the binary heap, which is a complete binary tree where the value of each node is greater than or equal to the values of its children, also called a max heap. Let's dive into the C++ implementation of heapify and heap sort. Let's explore STL sorting functions. The C++ standard template library provides efficient, ready-to-use sorting algorithms that are optimized for different use cases. Some of the functions are standard sort, which is a general-purpose sorting algorithm, intro sort that is a hybrid of quicksort, heap sort, and insertion sort. Standard stable sort, which maintains relative order of equal elements. Standard partial sort, which sorts a specified number of elements. Standard nth element, which partially sorts to find the nth element. The code shows how to use these STL sorting functions with a custom comparator. Now let's do a sorting algorithm comparison. Choosing the right sorting algorithm depends on your specific requirements. Here is a comparison to help you make the right choice. Bubble sort has a time complexity of order of n squared, space complexity of order of 1. It is stable and best for educational purposes and tiny arrays. Selection sort has a time complexity of order of n squared, space complexity of order of 1. It is unstable and best for small arrays, minimizing swaps. Insertion sort has a time complexity of order of n squared, space complexity of order of 1. It is stable and best for nearly sorted data and small arrays. Merge sort has a time complexity of order of n log n, space complexity of order of n. It is stable and best when stability matters and linked lists. Quick sort has a time complexity of order of n log n, space complexity of order of log n. It is unstable and best for general-purpose arrays. Heap sort has a time complexity of order of n log n, space complexity of order of 1. It is unstable and best when memory usage is a concern. Standard sort has a time complexity of order of n log n, space complexity of order of log n. It is unstable and best for most general cases in C++. For most practical applications in C++, using STL standard sort is recommended, unless you have specific requirements. To optimize your sorting implementations and make the right algorithm choices, follow these guidelines. Use STL algorithms for production code unless you have specific optimization needs. Consider data characteristics such as size, distribution, and whether it's nearly sorted when choosing an algorithm. Use stable sorts when preserving the relative order of equal elements is important. Benchmark different algorithms with your specific data before making final decisions. Here's an example of a custom comparator. For further learning, use the C++ reference documentation. You can also take algorithms and data structures courses, participate in competitive programming platforms, and use algorithm visualization tools. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.